Okay, so let's look into question number 38 from the sample paper given by the GATE authority. So this question is from linear algebra, and if I talk about the topic, so it includes two topics. So one is the uh, four fundamental spaces and orthogonality. So if you look at the question, then it is asking about the some orthogonal relation between the four fundamental subspaces. Okay, so let's read the question. What question is asking: that given a matrix of m by n, the following statements are made regarding the matrix A. So statements are given. The statement P column space is orthogonal to the row space. Is statement Q, the column space is orthogonal to left null space. Statement R, the row space is orthogonal to the null space. Statement T, the null space is orthogonal to the left null space. And it is asking which of the statements are true. So this question is purely based on the fundamental theorem of one of the fundamental theorem of the linear algebra. When you look into the chapter orthogonality, then there you will find that uh, the relation between these four fundamental subspaces. So how I will proceed with, I will first tell you the answer, what is the correct answer for this. Then I will take a simple example where I will find the four fundamental spaces, and I will visualize those four fundamental spaces with a specific example. There you will have some kind of visualization that which subspace is orthogonal to which subspace, right? So the correct answer for this is the option Q and option R. So what does the option Q says? That the column subspace is orthogonal to left null subspace, and option R says that the row space is orthogonal to the null space. So Q and R is the correct answer. So according to that, option C is the correct answer. Now let's take an example and let's visualize that how this column space is orthogonal to left null space and how this row space is orthogonal to uh, the null space. So here I have taken an example. So I have already solved this example and I have already found the subspaces of this matrix, that is matrix A. And so how we can find the four fundamental subspaces? So to how to find the four fundamental subspaces, if you look at my last video where I have taken an example and I have gone through the each steps, and there I have found the dimension of each four subspace and the basis for each four subspaces. So from there, from that video, from the last video, you will get the idea how to find those dimensions and the subspaces and the basis for those four subspaces. So, and what are those four subspaces? For that you will obviously have to go through lot of videos, and then you will understand of what is the column space, what is the row space, what is the null space, what is the left null space. So for that you will have to cover a lot of things, and then you will have the visualization of these four subspaces. But I will pick this specific example where I have taken this matrix A, and what I will do, that I will find the subspaces, these four subspaces of this matrix A. So let's look at this, the column space. So column space of A. So if you see that the number of pivots in this matrix A, that is this 1 and 2. So we have the 2 pivots, then we can say that the rank of this matrix is 2. And if we know the rank of matrix, then we know the dimension of the column space and the dimension of the row space, and that is equal to the rank of the matrix. So the dimension of the column space will be 2. Right now, since we know the dimension, or the other definition of dimension is that how many vectors in the basis. So let's find the basis for this column space. So if you look at this matrix A, then the pivot columns are this C2 and this C3. So we will pick these two vectors as our basis. So we have picked these two vectors as our basis, and if you look at the basis of the column space, we have the two vectors, right? So number of vectors in the basis, so we have the dimension 2. Now if you look, you are in this RQ, right? Because we have the, if you look at the any column, we have how many components? We have 3 components, right? So we are in R3, and we have got the column space for 2 vector, right? And these 2 vector, what they will span is the XY plane, right? So they will span the XY plane. Let's keep it in mind. We will also draw this column space. Now let's look into the row space. So if you look at the row space, that is nothing but the column space of A transpose, right? So row space is nothing but the column space of A transpose, or you can say the row space of A. It will have the same dimension, and let's find out the basis. So for that, if you look at the columns, rows of the matrix A, then it has the pivot and this one has the pivot. So we will select these 2 vectors as our basis for the row space. So this is the basis for the row space, and if you look, then these two vector are spanning YZ plane in RQ, right? Because if you look at the components of the row vector, then we have the 3 components. So they are these two basis vector are spanning R square, that is a plane in RQ. And what plane particularly? Then specifically I say which plane? Then YZ plane. So let's keep this in mind, that row space is spanning YZ and the column space is spanning XY plane. Now let's look into the null space. So how we find the null space is, we look at the combination, like if I say AX is equals to 0, then how we find the null space of this matrix, that we look for the combination, we look for the axes that make the rows, that make the columns of the A to 0. So what combination of columns of A will give you this 0 vector? So that what we call the null space. And if you look at this matrix A, then you will find that you have this 2 pivot column, that means that are the pivot variable, and we have the 1 free variable, right? So for free variable we can select any number, let's pick 1. Then by back substitution you can find the other 2 pivot variables. So we have find x1 1 and x2 0 and x3 0. So now this spatial solution, we can consider this spatial solution as the basis for the null space. And if you look at this vector, then it is nothing but the x-axis. So null space is spanning the x-axis. Now let's repeat our subspaces, that the column space is spanning xy plane, the row space is spanning yz plane, and the null space is spanning x-axis, right? Now let's look into the left null space, and what we look into the left null space is the we look for the A transpose y is equals to 0. So in words, if I say this, then rows, then what combination of the columns of A transpose will give a 0 vector. So so in last video, if you see, I have explained way of finding this left null space. Since this example is trivial, or I can say this example is easy, then you can easily find that what is in the left null space. You can see that this matrix has row 0 0 0 here. So in the basis for the null space, left null space would be this vector, that 0 0 1. So how we find the left null space, how we find the basis for the left null space, you can look my last video. There you can get the idea how we can find the left basis for the left null space. So this is the basis for the left null space, and if you look what this left null space is spanning is the z-axis, right? Z-axis. Now let's summarize what are those four subspaces. Column space is spanning xy plane, row space is spanning yz plane, left null space is spanning z plane, and null space is spanning the x-axis, not the z plane but the z-axis, and this one is x-axis. Now if you see that, let's look at this, the spaces that they are spanning. So this xy plane that is in pink color, so that is the, obviously that would be the infinite plane, and this is the column space, right? This is the column space. So this is the column space that all the vectors will be in xy plane. All the vectors that is in column will be in xy plane, and we found those two bases also, right? Those two bases will span this xy plane. Now if you look at the row space, this is the row space. So row space is yz plane, right? So this row space is yz plane, and the null space is this z-axis, and the left null space is this x-axis. Now let's look into the book and let's look at that fundamental theorem. So that question was directly from this fundamental theorem. So what does this fundamental theorem says? That the null space is orthogonal component to row space, right? And the left null space, that is null space of A transpose, is orthogonal components to column space. This is the direct theorem that was in the form of a statement in the question. So now if you look at the picture of this theorem, so how the author have shown is the row space of A, and that is perpendicular to the null space of A, and the column space of A, and it is perpendicular to the null space of A transpose, that is the left null space. Now we have solved a specific example, right? Now let's look at those picture. Are we justifying that or not? So this is our column space, and according to our theorem that the left null space should be perpendicular to our column space. So we have the column xy plane, right? So the column space is xy plane, and the left null space is z-axis, right? Left null space is z-axis, and these two are the orthogonal subspace. So this is not the null space, but this is left null space, right? Z-axis, and this one is null space. So this is the column space, right? That the pink one, and if you see that the left null space, that is the z-axis, that two subspaces are perpendicular, right? This Z and this column space, right? Now the what does the second statement says, that the we have seen that this column space is orthogonal to null space of A transpose, or left null space. Now the row space of A should be orthogonal to null space of A. So row space, if you look at the row space, that yellow one is our yz plane, and that is our row space, is spanned by the bases, those bases that are that is in the row space. So this, and if you look at the null space, that is our x-axis. So these are perpendicular, right? These row spaces and the null spaces. So here it was the specific example that we see that also that x, y, and the row space and the column space. So that was, I think, that justifies the theorem. So it was the specific example that that shows specifically, if we see that we are able to see the subspaces plane, I can say, and the subspaces line, and we also verify this that the row space of A is perpendicular to null space of A, and the column space of A is the perpendicular to orthogonal to null space of A transpose, or the left null space. Okay, so I think I have answered and explained the question number 38, and you have got the answer. And if you want to have the more explanation and more detail, then you can go through two chapter. That one is the 4 fundamental subspaces, and the second chapter is the orthogonality. Then you will have the broader broader visualization of this question. So that is all from my side. Thank you.